Hello everyone, welcome back to another video. Today we'll be talking about the concept of continuity and discontinuity. So this is going to feel like something that's a little bit strange in your limit chapter, but it's very important to understand because it's kind of how we define limits, and limits help define everything else. So it's just a nice bit of information to know. So when someone asks, what continuity is, when I ask them, usually they'll say that, for the entirety of a certain line segment, everything is defined. That's kind of what continuity would be, and that's a good idea to understand. Another way of understanding is that continuity is just this idea that there are no breaks in the graph. So if there are any breaks, that means that there is not full continuity. And if there are breaks, so breaks would be called discontinuity. That would be a good way of understanding discontinuity. And we want to understand that because we use this idea of continuity to understand kind of this main idea of how we understand if something is continuous. Because we just talked about this is a good way of understanding continuity, but we also can use limits to understand it as well. So something is continuous, or we could say that x is continuous entirely if these things are true. So if f of c is first exists, so if f of c exists or is defined, then we would say that's going to be the first thing. The next thing is we need the limit of that c value. So the limit of x of some value c needs to exist as well. So it also has to exist. So far, what do we have? Well, we have that for something to be continuous, we need first f of c to be defined. We need the limit to be defined. So basically, the function value and the limit both have to be, they have to exist. And the f of c, lastly, has to actually equal the value of the limit. That's kind of the final one. So if that's true, if the limit value equals the f of value, then we know that the function is defined. We would say that now the function is continuous. And that makes sense if we think about it, because if we recall maybe graphical limits, if we had some sort of discontinuity, we remember saying that the limit values were different than the function value, or maybe the two limit values, one side was different from the right, and in either case the limit value, they weren't the same. So because they weren't the same, we said in the graph that the whole thing wasn't it didn't exist. We said that the f of value of the limit didn't exist, and that's because it wasn't continuous. So now you can kind of see why it's important to understand these three things. They help us define if functions are continuous and later differentiable at certain points when we start learning about derivatives. But for now, let's focus on the limit part. So let's pretend the problems they'll like giving you for these, they'll like giving you a function, and they'll want you to say, what's continuous about it and what's discontinuous about it. So let's see. Let's just say we had f of x equals to sine x. Is this continuous everywhere? We would say yes. We would say it's continuous from negative infinity to positive infinity. And we wouldn't need to put discontinuity anywhere because it is continuous everywhere. So they might give you some functions where it is fully continuous, so we don't have to worry about understanding discontinuity, but sometimes they will give you something you have to worry about. So let's pretend we had something like 1 over x minus 2. So if we had something like 1 over x minus 2, is this continuous everywhere? No, it wouldn't be continuous everywhere, because we have this value here. If we put in 2, we would get 1 over 0, which would make it undefined. So we know it's not continuous everywhere. So let's first write that continuous statement. So we would say it's going to be continuous from negative infinity to negative 2, and then union, I apologize, from positive 2, and then from 2 to infinity, because 2 is the value that makes this an undefined function, right? This is like one of those rational functions where there's an undefined value somewhere in it, okay? So that's our continuous. And if you weren't sure how we made sure it was 2, just set whatever is causing the problem to 0, the zero product, and then you'll be able to get that x equals 2. This is our value, our discontinuity. So we would say that our discontinuity would be x is equal to 2, just as we put right up there. And we would say this is a we would say it's a removable. I apologize. We would say I wrote the wrong one. It would be a non-removable discontinuity. Why is it non-removable? Because we can't get rid of it, and that's why we label it as non-removable. So to kind of illustrate that, so we have the two types. We have a non-removable discontinuity, and we have a removable discontinuity. So what would be a non-removable discontinuity? Well, there's a few. So the first one would be what's called the jump discontinuity, and you've seen this already with graphing videos, I'm sure. So this would be a space in between a graph. This is a jump, and we can't get rid of the value. We can't get rid of it in any way. It's a big hole kind of in the graph. Okay, we also have what's called a infinite discontinuity. It looks like this. Usually it's an asymptote, and if you notice, this would be an infinite one because we can't remove an infinite discontinuity. There's nothing we can remove here. The only removable discontinuity would be a hole, and this is one point in a graph where the function doesn't exist. And this would be the only case we have a removable one because it doesn't necessarily hurt the function overall in every other place. Okay, so those are the types of discontinuities and how they relate to something being continuous and discontinuous. But let's see if we can show that the removable one in action. So if we had something like x plus 3 and it was over, let's just say, I don't know, x squared minus 9. We could rewrite this as x plus 3 over x plus 3 over x minus 3. So if you had to take a guess, we know that there's a discontinuity because if we put in 3 here, it will have a 1 over 0, an undefined value. But what would be defined? What would be the non-removable? What would be the removable? Because we know that our continuous statement is going to be something similar. We'll have these two values here because these are the things that give you a 0 on the bottom. These would make it continuous. These make the problem with the continuity. So if we were to put that here, we could say that it's continuous from negative infinity to negative 3. We would say union from negative 3 to 3, and then union from 3 to infinity. So the same thing as before, it's just we have two values instead of one. And again, we found that the same way. So if we set x plus 3 equal to 0, we'll get that x is equal to negative 3. So you can do it in your head, or you can just do it on paper. Both work perfectly fine. But if we wanted to find the discontinuity, specify the discontinuity of this function, what would we do? Well, if we wanted to figure out which is which, because we know both of them are discontinuities. We know x is equal to 3 is a discontinuity, and we know that x equals to negative 3 is a discontinuity. But how would we solve it for what's what? Well, we know that a removable discontinuity from our hole from before, so remember our hole looked like this, a hole would mean we could remove it. So can we remove anything in this? Well, we can. The x plus 3's can be removed from the expression, which means that the x equals to -3 is the one that's removable, because remember we have to solve for the x value. So the x equals to -3 is actually going to be the removable discontinuity, which means that of course this one's going to be the non-removable discontinuity. But the reason why it is that is because if we wrote the expression again, we'd have 1 over x minus 3, and this is what's left in the function, and it can't be removed, which means it must be the non-removable. And if we solved for x, we would get x equal to 3, which is why x equals to 3 is the non-removable discontinuity. So just keep in mind that when they solve problems with discontinuity and continuity, it's just a fancy way of asking you, do you understand that certain things can make a function not exist in certain areas, and can you write that for me at the end? So your answer would be this right here. So if they ever ask you these problems, this would be the answer, you specifying what's continuous, what's discontinuous. Okay, so that's your basic idea of continuity and discontinuity. Now, using that knowledge, they're going to introduce you a theory, or a theorem, I should say, that will help you understand kind of it relates to continuity. So it's called the intermediate value theorem, or IVT. And what it's really just saying is there's some value in between two other ones that exist given a couple things. So another way of saying this is we have, let's just say, a graph, and we have, let's just say, point A and point B, and let's just say the y value will be f of A, and then our other one will be f of B. Okay, and what we're saying is that we have a value k, which, remember, k is just f of c. So there's a value k that you will get guaranteed from a value c, which is like the x value, if two things are met. Okay, so we basically there's some sort of line, doesn't matter what it is, and there's this value, k and c, if a couple of things are met. So the first thing is we need the function to be continuous, which is why we had to introduce continuity before, because we kind of need to understand the concept of continuity to apply the theorem. We don't really use it to a huge degree, but we still need to understand it. The second thing we need to understand is k, which, remember, is f of c. So this is f of c. Is f of c between f of a and f of b? And really what that really means is they'll give you some two numbers interval, and you're just going to try to figure out, is your k value between those two? And if it is, we can solve for c, and we can find a guaranteed number in that. So that's all the theorem is trying to tell you. And even if this is a little bit confusing, the actual math involved in doing it isn't too bad for the theorem. Okay, so let's just say the problem usually will give you a function. So let's say we have the function f of x equals to, let's just say, x squared minus 6x plus 8. That works, and we want to find it on the interval 0 to 3. So what would we do? Well, first we have to check the two things. So is our function continuous? So is it continuous? And we would say yes, it is continuous. Why is it continuous? Well, if we plugged any number in, we would get something that it's a real value, but we also know that polynomials in general are continuous, so that's also why we can tell, but there are multiple ways you can check, but it is continuous. Okay, the second one is f of a, does f of a between is f of c, the k, is it between f of a and f of b? Well, let's check. So f of 0 first would be equal to 0 squared minus 6 times 0 plus 8, and that would of course just give you 8. Okay, now let's try f of 3. So f of 3 would be 3 squared minus 6 times 3 plus 8. Okay, so if we were to solve that, we would get 9 minus 18 plus 8. And of course, that would turn into negative 9 plus 8. And then negative 9 plus 8 gives you negative 1. So, and I forgot to give you it, but we want to, they always have to give you the value of f of c. So our f of c, or our c value, we want to test is going to be 0. So they have to give you the k value, but just know that they did give you the f of c value. We're saying that it's going to be 0. Okay, so if the f of c value is going to be 0, what we have to do now is we have the two function values of negative 1 and also 8. So is 0 between negative 1 and 8? It is. So the function check, the function applies. So now we can do the easiest part of the actual thing, which is usually doing the quick finding that c value. Okay, so we kind of have to work backwards. So we want to replace the x's with c's. That's usually how they structure that for you. So 6c, we're just replacing with c's. That's all we're doing. That's all. And we want to equal it to the f of c value, which in this case we said it was 0. Now it's not always 0, but for this case we just, whatever it's equal to, we just put that on the other side. That's it. So we could factor this expression, and we would get that it's equal to, we have c minus 4, and then a c minus 2. And the reason we could tell, if you forgot a little bit of how that works, if we just kind of put over here, what two numbers will add up to give you negative 6, and also will add to give you, or multiply to give you 8. Well, negative 4 times negative 2 is 8, and negative 4 plus negative 2 is negative 6. So just in case you forgot, that's how we got those two numbers. If we solve for it, we'll get that c is equal to 2 and 4. So we're done, right? This is our answer. We found our c value. That's what we want, right? Almost. We have to make sure that both of these values here are within the interval that we said from the beginning. Because remember, the theorem is saying that these values exist in this interval, not outside of it. So, is 2 within our interval here? It is. Okay, is 4 within it though? No, 4 is outside the interval. So we would actually say that c is only going to be equal to 2, because 2 is the number that is in the actual interval. Okay, so this is how you would use the intermediate value theorem. All you have to do is make sure it's continuous, make sure that the two y values of whatever points they give you on the interval are between whatever f of c or k value, as they might put it sometimes, that they give you. And if those two things are correct, you just have to equal the function to whatever f of c value, solve for c, and just make sure that whatever c values you get are within the interval. Okay? Okay. The last thing I want to do, which involves continuity, is what's called, it's essentially a process that deals with just checking understanding of continuity. It's going to feel a little bit different from before, but we're kind of jumping around to understand all these concepts of continuity. So let's say we had something like might give you a function, and it kind of might look strange at first, but it's called, let's just go with, it's like 2 and then e to the a x. So I know there's two variables in there. Don't worry, it's not too complicated actually. And it's a piecewise function. So we're going to say it's from less than 4, and then the other one is going to be the ln of x minus 3 plus x squared, and that's going to be greater than 4. So they're going to ask you find a value that makes this continuous. So find the values of a that make this continuous. So whenever they give you this kind of weird question, they're really just asking you to equal these two things on the piecewise function and then to solve for a. So let's do that, okay? So we'll get 2e to the a x minus 2 equals to ln of x minus 3 plus x squared. And now let's just substitute 4 for that, right? So 2 times e, so this would be 4a. We're just, so whenever there's an x, we're just putting a 4 there. 4a minus 2 equals to the ln of 4 minus 3 plus, of course, 4 squared. Okay, so all we're doing, we just substitute it back in, and that's it. Okay, so now let's see if we can simplify anything. So there's nothing much we can do right here yet, because this has the a in it, so let's bring it down for now. And then let's go ahead and simplify the ln. So ln of 4 minus 3 is the ln, just remember, of 1. And if you didn't know, the ln of 1 is just going to be 0. So it's going to be 0 plus 16. So really what we have is 2e to the 4a minus 2 equals 216. What should we do now? Well, we want to get closer and closer to the a. So let's add 2. And after that, we're going to divide by 2. So we'll get e to the 4a is, or 2e to the 4a is equal to 18. We're going to divide by 2. Then we'll get that e to the 4a is equal to 9. Then we'll take the ln of e, because the e gets canceled out. With an ln, that's usually the easiest way to get rid of it. So we will just have the 4a is equal to the ln of 9, which remember is fine. This is a number. Ln of 9 can exist there. That's okay. It doesn't have to simplify. Then we're just going to divide by 4, because we had that 4a over here. So ln of 4 divided by it. Then we're going to move it up here just so I don't run out of room. So with an a is equal to the ln of 9 over 4. And this is going to be the answer. So we actually solve the problem. So when you get weird problems like this, I know it seems odd, but all you're doing is they're going to give you like a piecewise function, and they're going to ask you to find, what makes it continuous, and you're just going to take whatever x value they give you in the piecewise function. So in this case it was 4, and then you're going to plug it in to the x value once you equal the two to one another. Then you're just going to solve for a or c, it may be c, like you would for x, and then you'll get a value. It might be kind of weird. I picked this example because the answer is kind of weird, but it's just a number. You could plug this into your calculator and it would just be kind of a longer number. And that would be it. So this is kind of the concepts of continuity that they'll give you for your limits chapter usually. Just keep in mind that limits are important, and continuity helps define limits. So if you were going to understand kind of a review of what we did, remember the main thing is continuity, or we discussed the different types of continuity. So we talked about the jump, remember, we talked about the whole, we talked about the infinite discontinuity, we talked about how they are non-removable and also removable discontinuities. We talked about how we might get functions that might produce certain discontinuities and continuities, and we have to specify, where it's continuous and then where it's discontinuous. Then we talked really about the intermediate value theorem, which remember isn't too bad. We're just trying to test you on the ideas of what continuity is, and you're trying to find a c value that exists in a line. And finally, we just talked about two functions where we're trying to find an a value that makes the whole thing continuous, and just like before, we find continuity by equaling them to one another and plugging in the x value to which they kind of overlap. In that case, it was a 4. So, these are all the topics of continuity. I may have videos later on that go a little bit deeper on other examples, just going a little bit more practice for each one, but this is a good overview of everything to do with continuity. All right, thanks for watching.